Sir, are you ready?
So shall we start?
Yes, we can.
Yeah. Okay, Renuka madam.
Very good evening to all. I, Renuka Pawar, wholeheartedly welcome you all on behalf of the organizing committee at Bharati Vidya Bhavan, Sardar Patel Institute of Technology, on the 8th day of AICT sponsored 2-week online faculty development program on data science and its application. I take this privilege to warmly welcome Mr. Pawankumar Fakatkar. He is an education specialist in education and competency development at KPIT Technologies Private Limited. He has done a master degree from Sardar Patel Institute of Technology, Mumbai. He has done various certifications, including deep learning with MATLAB, MathWorks machine learning with MATLAB, MathWorks programming Xilinx ZYNQ, SOCS with MATLAB and Simulink, MathWorks generating HDL code from Simulink, MathWorks MATLAB fundamentals. So once again, I welcome you, sir. May I please request you to take over and start the session? Over to you, Pavan Kumar, sir.
Thanks, Renuka ma'am. Um, Let me start. I hope I'm visible and audible as well, and you guys can see me properly good. And I will start sharing my screen in a moment. Please let me know when the screen is visible. I will also use the chat box today for having a conversation with all of you. So if I ask a question, I'm expecting that I will get the answers on the chat box. Either yeah, just a second. Let me adjust my screen. Hmm. Well, I'm using dual monitors, so I'm parallel. If I'm looking over there, I'm actually looking at you. Okay, so I'm just putting a question. Am I audible? It's a dummy question that I'm asking, and say if I'm audible, or if you want to give an answer, I would like you to answer it in the chat box over here. This is the medium that I will be using in today's session to communicate with all of you to get your answers, and I want this session to be interactive so that it won't feel like because we have a 2 hour session today, so it like it's a monotonous session where I'm just keeping on talking throughout this 2 hours. So please make sure that whenever I ask a question, give an answer. There's no right or wrong answer. It's just that there's no answer which is going to bother me today. So I'm putting my screen in slideshow mode, and I hope my screen, face, and audio, all of them are in a proper sync. Okay, good. Um, After a moment, I will stop sharing my camera just so that I can save my bandwidth and CPU usage. So that because there are some simulations that also I would like to show at the end of the day. So yeah, let's just get started. All right. So hello everyone. My name is Pawankumar Fakatkar, and I work as an education specialist in education and competency development team at KPIT Technologies. In short, I am a teacher, but I teach only to students who have already joined the organization and teach them on the advanced workflows for automotive domain like powertrain, autonomous driving, model-based design, control system, math modeling, and so on. So these are my area of expertise in the current organization, and I train a lot of say fresh engineers and senior engineers on these workflows over here. And today we'll be talking about some of the AI case studies on autonomous driving. Um, just curious to know about what were you expecting when you heard that you will be attending a session called AI case studies on autonomous driving by someone from an automotive company. What was your thought process? You can put it in the chat box, and I can use that as a cue. If let us say there is a certain topic that I'm not going to take today, I will inform you in advance, and I will set the right expectation right from the beginning. So any high level thoughts, what you are expecting, you can put it in the chat box. I'm curious to see that. And again, to make this session successful, there is the only key, and that key is interaction. So I want all of you to talk to me today. So I hope Okay, can we trust autonomous driving? That's a good question. I would rather say, how can we design an autonomous system that we can trust to some extent? Yes, driverless car. Yes, that's the theme of today's session, and trying to understand the nitty-gritties of that. Just a question out of curiosity. Hey, so although I said that I will be delivering the session, I'm asking you a lot of questions today. Um, what all things did you learn in past few days? I will try to link today's session with whatever you have learned so far. So you learned about neural networks, yes, machine learning, deep learning algorithms, some tool chains. Yesterday, I think there was a session from MathWorks. I will be using MATLAB today, and just curious to know what all things you have learned so far. So I will stand on top of your current learnings. You can just put the thing that you liked in the current say FDP, so that I will try to revolve my discussions around that. Can you put it in the chat box, all of you? I am getting answers from two of them. Okay, machine learning algorithms. Thanks, Indrajit sir. Deep learning, neural networks. Okay, Gofne sir. Yeah, come let's get RNN. Okay. All right. So yeah, this is good for me to get started. Um, so today what we will see is this is going to be a two-part session where we will talk about the infrastructure inside an autonomous car and how that infrastructure will be used in such a way that you can feed the data that is collected by this car into a processing system and certain control actions will be taken. So we'll divide this into two parts, which is first one is understanding the infrastructure, and then we will start with the actual control of a car. And I will try to demonstrate some of the niche applications in autonomous drivings, which are popular in the industry right now, and we will see how those applications are built from scratch. So today it will be more of a discussion on the infrastructure, and I will end this session with one control application on how we can design a mathematical model of a car, and how can we design an application like adaptive cruise control. And tomorrow we will see how we can merge the deep learning algorithm that you have learned so far along with this control system algorithm, and make sure that both of them together are going to have or at least give you one level one uh, system for say cruise control of a car. Okay, so that's the kind of application that we'll be looking at. So one that I'm sharing today are not from my organization. I'm here in the say capacity of someone who is from the automotive industry and someone who is close to academia. And I would like to demonstrate the public domain knowledge, or share the public domain knowledge with all of you in such a way that you are prepared for the future of autonomous driving. So let us see some simple application of a self-driving car. And here I will stop sharing my screen. Sorry, I will share my screen. I will stop my video so that there won't be bandwidth issues. Okay, good. So let us see this application first. Okay, here you can see the person has entered the drop location, and he or she, I think he is not touching the steering wheel at all, and still the car is capable of navigating from point A to point B with all the infrastructure that is inside this car at this time. Okay, so this is a popular car called Tesla. Um, and you can see the application where the person is not even touching steering wheel from beginning. So someone mentioned a driverless car, Aparna ma'am. So when we say driverless car, actually there is a driver sitting over there just as a safety precaution, because you cannot have completely say a driverless car yet. We are yet to reach that stage, but this is the driver is there for say safety of vehicle, pedestrian, and other say fellow drivers on the road right now. But the car you can see is completely running in autonomous mode. So I have a question for all of you. What is happening at the background in this car? What all things do you think is present in this car which is letting this happen? Your high level thoughts, you can share it with me in the chat box. What do you think is present in the car that is letting us do this? What kind of infrastructure is there? Navigation, yes. So there is a kind of navigation system, GPS or GNSS system, which is letting us do this. Camera, yes, the entire system has multiple cameras, which is say taking the information in real time and accordingly decisions have been taken. Yeah, sensors, yes, there are a lot of sensors. So controllers for control, steering, pedal, accelerator, motors. Yes, these are all the things that are being controlled in the background. So we'll see how this kind of control actions can be taken. But yes, that is also a part. Um, is there any a niche sensor that you have heard of which might be present in this autonomous system, like radar, lidar, odometers in our car? So today, yes, we'll see what kind of sensors are present in this car. Although, yeah. So here you can see that all the answers that you gave are absolutely correct. In fact, we have these sensors. In fact, we also have ultrasonic sensor, which you can see over here. So this is a reference taken from Tesla's website. We are just looking at that. So in this car, there are multiple sensors like radar, which is capable of detecting an object up to 160 meters. Then you have forward-looking side camera, which is this is the region in which it is active, whose maximum distance is around 80 meters. Then you have main forward camera, whose distance is around 150 meters. You have also a narrow forward camera, which is around 250 meters, and then there is ultrasonic sensor, which is capable of detecting up to say 8 meters, which is good for all weathers and say lower distances like parking applications or say navigating at a turn or say taking checking blind spots and so on. And then there is rear view cameras, which is also giving you data about this car. So you can see all 360 degrees of this car are being monitored by the number of sensors that we have at this time. And you can also see that uh, there is no blind spot which is left. In fact, uh, uh, there is a theory that people say in future there might be a possibility that we can design a complete autonomous car just by using say image sensor, that is cameras, and there won't be any necessity of sensors like radars and lidars, but there is a technology limitation at this time, and say um, technology limitations in terms of the resolution and say in terms of how much data can be processed at a given point of time. And then there is a limitation of algorithms. Although we design the best of the best algorithms for say working with this data, there is a high chance that you won't get the best outcome from that kind of sensor. So these are sensors on say the one of the best cars out there, and we can see what is happening in that car over here. So here you can see a small video, which is a repetition of the previous one. And here you can see that all the cameras or say images that were captured, the car was able to detect all the objects from all the directions, and it was taking its decision in real time on the basis of that. You were able to see. So let's go a little back. Here you can see the sign for stop. There was this stop sign just a moment ago over here. So you saw that the car went a little slow and then it caught up the speed. Okay, so that was an instruction. You can see the lanes on the road. You can see all the say crossing marks, um, the road signs, and also parallelly you can see in this video at the right hand side that these objects are detected and accordingly the actions are being taken. Okay. Well, this is a long video. I will try to say videos with you, or at least the link for this videos, and you can actually see this things in action. So let us try to demystify. Accidentally, I showed you the answer. So what do you think is happening in the background? Um, do you think so? Whenever we design an algorithm or say design a system, we have a flow chart, right? What do you think is a possible flow chart for the system that you just now witnessed? Anyone? Any random guesses you would like to talk about that? What would be a possible flow chart of say an autonomous vehicle? What do you think is the first step in the previous system that you just saw? Okay, start the vehicle. Yes, that's a very nice answer. Start the vehicle. Good. And once we start it, our only say task is to give a position, the end position, right? And once we do this, what the car starts doing over there? It starts acquiring data from sensors, right? Thanks, sir. So we start acquiring the data from our camera, and that camera will identify obstacles. Absolutely. Thanks, Vandana. So we will identify the obstacles in the car. Then, on the basis of this, say obstacles, what do we do? We have identified everything, all the obstacles, like all the cars, all the pedestrians, say road signs, if there is a curb on the road, all these things are detected. What do? We try to identify our current position, right? On the basis of that, we will be taking some action in the future. Obstacles can be person walking on the road or other vehicles. Absolutely. So using this data, we generate control signals. So yes, sir. So what we do here is we identify our location. On the basis of that, we design a control algorithm, or say a plan that how are we supposed to go ahead. So as Chetna ma'am said that we start with slow speed. It is one of the actions or say plan that we have in the current situation. And once the plan is say prepared for our system in the say hardware that we have, like a GPU based system or a computer inside the car, we generate the control signals, and accordingly the control signals will ensure that the car is proceeding. For instance, say if there is a pedestrian which is going really slow, we would either stop, so a control signal for stopping the car is generated, or we have to say proceed slowly. Slowly and steadily we are increasing the input for acceleration, and say if there is an open road now, we will go ahead with the normal speed or operating speed for that particular lane. So all these informations are say processed in a linear fashion that we discussed just now, and these are the components of an autonomous vehicle. So we start with perception, that is understanding our current or say capturing as much data from the environment that we have. And then there is the next step, that is localization, which ensures that we capture the data of where the car is with respect to its environment right now. And then we start planning our motion. What should be say the rotation that our steering wheel should have, at what speed should we proceed, and say how should we go ahead. All these things are being planned at this stage, and then we do the actual control action. And believe me, all the steps are done so quickly that we are able to say see them in real time as a final output, which happens in a say few seconds. Okay, so if we say summarize this, perception consists of say collecting all the low level sensor data, like your camera, radar, lidar, and then you have to perform something called as sensor fusion for collecting the data at the same time, and give this information to the next step, that is localization, in such a way that you have objects that are detected, lanes that are detected, and then localization is the process to understand where your car is present in the environment at the given point of time. And this is actually an essential step. Someone said that getting the navigation was one of the answer earlier. So we actually take the data from the map if it is known, or we create a map from the current situation, and then we plan. So what kind of actions have to be taken, and finally we take the control action, which means that giving a command for say steering, accelerator, brakes, and so on. I hope everyone understood the components, and what we are going to do is in next today and tomorrow we will demystify all the individual steps that we are seeing over here and take our actions accordingly. So let's go ahead. Yeah. Um, One important step that I would like to tell you is that um, if so this particular discussion is quite complicated, and there will be certain points that will be say difficult for us to absorb. So I have a small taxonomy. I would like to explain this keywords right in the beginning so that you will be able to relate with the point that I'm mentioning in future, and if and when needed I will say recall that concept whenever we are talking about a certain application. So when I say ego means the car itself, which is being controlled at this time, and it is opposed to say other vehicles which are in our environment. And generally, when I will say that our ego vehicle is collecting the data, which means that the car that we are controlling is now collecting data, which is say going to run autonomously. So that's the definition of ego. Then we have are sensors like lidar, a type of sensor that transmit light, and say it returns the light, and the measuring return time, and it shifted or it shifts will give us the information about all the positions, and say the geometrical understanding of our surroundings. Then you have radar, which say transmits your say radio waves, and the time by which it is returned, we understand that if there is an object in front of us. And a similar thing for sonar sensor, which is sound navigation and ranging, where instead of light or say RF waves, we transmit sound, and we capture that back and understand how much distance is there. So all the sensors that you saw in second slide, uh, these are the definitions for that. Of course, Tesla does not use a lidar sensor, but lidars are quite popular in the automotive industry, so or autonomous driving industry. So I always I'm going to take example of lidar. Yeah, let's go ahead. Then we'll also talk about control actions, and for that, we will also talk about PID control today. These are like three gains, where proportional gain is going to say control our output based on the amount of error that we have. The integral gain will control our output on the basis of accumulated error, and the derivative gain will control our output on the error rate change. So when I'm going to talk about or discuss about this cruise control application, I will actually demonstrate this in action to you, how this PI and D controller gains work together. Okay. And then we have this ODD, which is my operational design domain, which is like the set of conditions in which our car or say system is designed. And let us say I am designing my autonomous vehicle for an urban setting, or say for driving in a highway. So you can say that the car is designed for a highway setting ODD, or you can say it is designed for an urban setting or an urban environment ODD. And then there is next definition, which is object and event detection and response, which is the ability to say detect an object on the road, and say how you are going to take or an event will happen, that is take an action on the basis of the detected object, and say react accordingly to that situation. For example, if there is a pedestrian on road who actually came suddenly, you have to detect that object correctly, and then take the action of applying brakes. So that phenomena is called as object and event detection and response. So we will talk about this in our perception chapter. So I'm just telling you this. And finally, there is something called as lateral control and longitudinal control. So I will talk about this using a small diagram. Let me see if I can draw things over here. Good. I have a pen. Okay, good. So let us say I have a car running on, say, this road. Okay, so this is we are talking about our Indian road over here. We are assuming that the roads are really good right now. There is lane marking and we can follow it. So when I say lateral control, I am going to make sure that my car's steering is controlled over here. So say I am going to another lane, okay, and to overtake someone, okay. Let us imagine there's a car on the road. So we just jump into other lane, go over here, then come back. Okay, so that is a kind of situation that we come across almost every day around us. So in this case, what we see is that we are doing a lateral control of our vehicle. Whereas, if I say, do I have an eraser over here? Yeah. So let us go with our longitudinal control. And today we will see an example of longitudinal control. I'm repeating this multiple times, but let me tell you. So when I say I'm doing longitudinal control, which means that what we are doing here is whether we have to accelerate our car, whether we have to apply the brake, whether we have to say modulate our speed of our vehicle, all these actions come under longitudinal control. Everyone understood until this point all the definitions with respect to a car, what kind of sensors are there, and the taxonomy with respect to lateral and longitudinal control. If yes, please put a yes in the chat box so I can go ahead. That's a very good input for me to go ahead. Yes, no, maybe, perhaps. Good. All right. The last definition for going ahead is in terms of planning. So you might have two types of plannings in your car, which is a short-term planning and a long-term planning. So when I say that I'm going from Mumbai to Pune, and if a car has to decide that, then there is a long-term planning that which is a route that you're supposed to take. And when you are doing a short-term planning, then that kind of planning is like whether I have to apply a brake or not, whether I have to accelerate, whether I have to take a left or right turn, and things like that. So this comes under short-term planning. So where are we supposed to bring autonomy in the car? Because you are seeing so many applications of deep learning today. When we say that we are bringing autonomy using deep learning, so this is the question that we always have. So you either bring autonomy in your car for lateral control or longitudinal control, or you bring autonomy driver and so on. Okay, so these comes under OEDR, where we bring the autonomy. Then you have a complete, say, operational design domain where you are bringing autonomy so that your car will be going will run in any environment, like say all terrains, like urban environment, highway lanes. It will run properly in, say, crowded city and so on. Or you will have a restricted ODD. You can say that autonomy is only brought for highways at this time. We are not sure that how this car or autonomous driving algorithm will work in an urban environment. Okay, so these are the two places where we bring autonomy in a car, and these are the places where we bring the deep learning or AI algorithms, where the actions will be taken. Okay, just give me a second. I there is a yeah. Yeah. Okay. So now what we'll talk about is the levels of autonomy in a car. Sorry for the glitch in between. My mouse was not responding. It is doing very well now. So let us talk about the level of autonomy in a car. What kind of autonomy is brought in the industry right now, and what can you think of as an application that we are going to design together in next 2 days? So first level is no autonomy whatsoever. It is like the basic car that we drive on our roads today, like an older car that you're seeing over here. You have no autonomy in any kind of control. Human is going to be the responsible person for driving this car. And the next level is assisting the driver for your, say, either longitudinal control or lateral control. So if I say that this car is at level 1 autonomy right now, you will take care, or the algorithm will take care whether this car's, say, speed is being controlled right now or not. So that's either one part, or you can say that you go from one lane to another, which is lateral control, which the car is capable of doing. Okay. So when you say level 1, again, I will repeat this. It is either longitudinal or lateral control. And one important aspect over here is that the driver always require monitoring. The driver cannot, say, be careless in this case. Um, any example of, say, level 1 autonomy that you have seen in a modern commercial car around you so far? Um, just give me a second. Yeah. I hope I'm audible because I'm not able to see this WebEx screen. Wait.
Pawan, you are audible. No problem.
Yes, no problem. Right.
Audio,
Okay.
video, yeah, yeah. Audio, video, no problem. No problem at all.
Okay. Great, sir. Thanks. So, yeah, I was a bit worried. Yeah, let's go ahead. So, now, can anyone tell me what is the possible application that you have seen in level 1 autonomy so far as a commercial product that is available in the market? Any high level guesses that you have? Any application that you have seen in your day-to-day life? And
Yes,
that,
yes.
yes, sir.
Yes, go left, go right, go straight. GPS. No?
Mm, well, that is, say, an application of ADAS. So it is Advanced Driver Assistance System, as we can define over here. In level 1 autonomy, we actually do the control action. And one example of, say, actual controlling is automatic cruise control. Have you heard about this application in, say, modern vehicles? Say, I have seen some applications in modern cars or mid-range vehicles like Creta or Ford EcoSport, where you have automatic cruise control. You enter the speed of 80, and automatically the vehicle will start running at the speed of 80. All you have to do is just control the steering action of the car. So that is one example of level 1 driver assistance. Yes, so it was something you have heard about, but now you are able to relate that, okay, this is the level 1 autonomy that is available around us. And here you can understand from the cost segment also, or say cost perspective of a car, that even level 1 autonomy is one of the expensive features in the mid-range vehicles today. Okay. Then comes the next level of autonomy, that is 2, where you have, just a second, yeah, where you have partial driving automation. So in level 2, both the tasks are done parallelly or together, which is lateral and longitudinal control. But again, one important thing here is the driver is supposed to keep monitoring the entire situation. The drivers are not allowed to sleep the way you saw it in the Tesla car just a few moments ago. So you have a complete control of lane changing, maintaining the speed of the car, on the basis of the input that we are getting from our sensors. The next step is um, the conditional driving automation. Okay, here you have the same level of automation that you had in level 2, But in this case, the driver is supposed to take the control only when the driver is alarmed. So let us say I am reading a newspaper or watching a movie when the car is being driven. But in this case, if say there is a pedestrian or a car which is detected by our radar or say by our image sensors, an alarm will be raised. And what happens here is your driver will start immediately taking the control of the car and make sure that the vehicle is running properly. Okay. This particular level of automation is actually controversial in the industry today, and a lot of say regulations are running around that, because we are still trying to reach up to level 3 as say the community of researchers and automotive domain people at this time. The next level is say high level automation, where the emergencies are handled by the car, but it still require driver control. So say this is kind of say the driver have a limited or say the car or autonomous algorithm sorry autonomous driving algorithm has a limited ODD. Can anyone help me recalling what is ODD? ODDs are operational design domain, which is the set of conditions in which we have trained our algorithms. And there is a limited number of ODDs in which the system is designed. Also, the driver is supposed to have some control on the car still, like the driver can still watch movies, say have a conversation on his phone or his her phone, and the car will take the action. And finally, we have level 5, which is like going to be a game changer in the world of autonomous driving. And in this case, we have unlimited ODD, which is your car is capable of running on any condition, urban environment, highway conditions, say traffic, city or say crowded conditions like what we have in India. All the situations, the car is capable of having or controlling itself. I mean, this is the future. It is not implemented yet, but still we know that there is a level which is defined for the car for this situation over here. Okay, so let's move back a little bit, try to see what are the components of the autonomous vehicle and how all these levels one by one can be achieved by us using the AI algorithms, the say physics of a car, and the control algorithms that we have at a given point of time. All right, so the first component that we have is perception. um, Next one is localization, planning and control, in which we have a lot of inputs given to our ego vehicle, which is say the vehicle which is being controlled right now, and the input that we have, that is from cameras, lidar, radar. Your environment is being monitored continuously, and then a planning will be done. So say you will decide on what kind of maneuver you have to do, and then you will do the driving action. So it's like a small summary of all the components together in a linear flow, and we will start say opening up this environment where maximum amount of AI is used, because today's session is AI case studies in an autonomous vehicle. Perception is a place where maximum amount of AI can be seen. Okay, and we'll talk about what kind of inputs do we get while working in an autonomous environment, driving environment. So our first component is perception. Um, and before I go with the perception discussion, I would like to redefine something, which is OEDR. So it is object and event detection and response. So this is the ability of a vehicle to detect the objects in its environment and then react to them appropriately. And this is one of the important criteria for automation in a car. Um, so when we say that we are doing perception, we say that we are trying to make the sense of our environment and where we are present in that environment. You have to identify various objects, track motion of a vehicle, and take informed decisions on the basis of all the say the objects that have been detected in the environment at a given point of time. Say okay, just a second. So I'd like to show you an interesting example with respect to that. So if we go to MATLAB documentation, what is exactly going on over here? Um, we have an application like object detection over here. Okay, so here you can see there's a complete algorithm. Here you can see that this is the input image to our system, and um, the algorithm which we have designed is capable of detecting whether we have a car or a pedestrian or say a lamp post and so on. So this kind of applications come under say perception. And what is the goal of perception at the end of the day? The goal is to differentiate between a static and a dynamic object. So if I take a look at, okay, just a second. Hmm. So if I take a look at this image over here, can you tell me what are the static objects in this environment and what are the dynamic objects? I would like to see the answers in the chat box for this particular discussion. Yes. So can you see any static or can you differentiate between static and dynamic objects in this image as a human? Can you do that for me, please? So a tree is a static object. Great. Pole. Okay. I would say lane on a road. People is a dynamic object. They are moving around, right? Like pedestrians or an animal that is coming in. What kind of object is a car? So, Jayashri ma'am, I would say that it is not a signal, it's an object that has been detected. The car is a dynamic object. Great. Mm, all right. So, signal stop, then static. Yes, sir. Um, it's a little, say, I won't say controversial, but I would say a gray area over here. We would say that, okay, my object is, or my car is stopped for 10 seconds at a signal, but we know that this object is a car, so we know that this is going to be a dynamic object, and when the car starts it will move around somewhere. So in that case we will try to predict its motion using its initial say action that it is taking at a given point of time. For example, it is just moving or started moving left. We'll try to predict that in 3 seconds the car will be say 10 meters or say at least 3 meters ahead, and accordingly we will take the action. So that kind of predictions we try to make, and then take our control actions. So coming back to our presentation over here. Hmm. Yeah. So we'll first discuss about static objects. So static objects is we'll differentiate further. So first we have say on-road objects like our road, lane markings uh, that we have. For example, if you have a road and this is not India, we don't see this happening. If there is a road, um, hmm, if there is a road on which there are say some zebra crossings which are very well marked, or say we have some uh, very bad lane that I have drawn over here. Yeah. So there is a lane which has been drawn like this. Okay, so these are the on-road objects that we need to identify. And let us say there is a construction which is going on, which is on the road right now, like this cones which look like VLC player, or say this curbs that we have on the road. Not curbs, but say stopping objects that we have. I don't know what's the proper name for that. So obstructions in simple words. Um, these objects are supposed to be detected by our AI algorithm, and we should take actions accordingly. For example, say this is something that happens around us almost every day. So we have a road, and one of the side of the road is completely digged up. Automatically, your car is supposed to go to the other lane, and then there will be, say, incoming traffic from here, and accordingly you should monitor the vehicle, and go back to the original road. That is one of the kind of on-road object that we are detecting. And then there are off-road objects that you are supposed to detect, just like curb, which is, say, the end of a road, which you are not supposed to go on, or say traffic lights, road signs like stop signal, or say there is a school ahead. All this kind of things should be, say, detected by our algorithm properly. Then we have dynamic objects, and in this case, I would say on-road objects like four-wheelers or two-wheelers. Um, Four-wheelers are pretty much safe. We can predict whether what kind of actions they're going to take. It is a little bit difficult in Pune, where I'm living right now, to identify what the person on a two-wheeler, or say a person who is on cycle, is going to do. So that is one of the difficult challenges. Also in autonomous driving, where the AI algorithm is supposed to understand what action the two-wheeler, or say a cyclist, is going to take. And then we have people who jaywalk. With jaywalk, I would say people who just uh, don't see the conditions on the road right now, whether there is, say, sign which is given, or there is, say, a crossing, or they just walk on the road without seeing on the right hand side or the left hand side. And we have to be careful of those on road objects. So as humans, we are really careful. Imagine what will happen if the computer is getting a control of that kind of phenomena. So yeah, that's one of the reason why designing AI algorithm for a car is difficult in Indian road conditions. And yes, it will take at least 20-30 years to come up with the technology that will be capable of handling this. And then there is this discussion whether we can call a four-wheeler a proper dynamic object, sorry, a static object or not. So it is only static when it is stopped. So I would not define this as static over here, but rather call it dynamic, which is going to move at least after some time from A to B position, and we have to take action accordingly. So I have this my car, which is, say, 20 meters ahead of, or say behind this car. I will know that in few seconds it will go from this position to this position. And accordingly, I have to plan my maneuver, and take a control action eventually. Okay. Then the next goal of my perception is localization. Understand where I am right now. So this comes along with the map that you have. So let us say I have a city map for my road conditions, and in this situation, I should understand that I am at a given point at a given time, and accordingly, my action should be taken. You should understand that what is my velocity, what is my acceleration, so that I can uh, maintain or control the speed of my car. And then you should understand what is the orientation of your vehicle, or say angular motion in which the car is moving. Okay, so what kind of sensors do we have for that will be feeding data into our deep learning algorithms eventually, and actions will be taken over there. So we have two types of sensors, that is exteroceptive sensors and then proprioceptive sensors. I know this is a tricky word. I have to practice it. So these two types of sensors are taken into consideration while taking all the actions, and these sensors will feed the data into our algorithms, which will take the action eventually. So tomorrow, when I will talk about how lidar data can be sorry, how lidar data is taken into the algorithm, or a deep learning algorithm, then it will be given to our actuator. You should be able to understand that this data came from a kind of sensor and what kind of output it is producing. So let us say we have designed the best of the best algorithms for our car today. Mathematically, these algorithms are perfect, but the output of these algorithms are limited by their sensors, or say limitation of our current technology today and we have to live with this limitation forever, and at least say next 20-30 years. In fact, in future, right now we have lidar sensors which are um, rotating and capturing all the informations. In future, or at least that's in the research phase right now, where lidar sensors are like solid state devices which will directly capture the output and do sensor fusion and give you a proper information about the current position. And it's a work in progress. In future we will have a better way to capture the information about our vehicles. So that is again limited by the sensor capability at this time, and still we are designing our vehicles using whatever technology we have at this time. Okay, so when I say I have something called an exteroceptive sensor, the first simple sensor that comes to our mind is a camera. Okay, the camera that we have, a dash cam, or a camera which is attached, say on the top of a car in front, or say on the blind spot in the rear. All the sensors, they are being monitored at a given point of time. There are a few metrics for a camera like resolution, field of view, the dynamic range, the lighting conditions in which a particular, say, car will be present in the environment at a given point of time. And there is always going to be a trade-off between, say, field of view and resolution. If you have a large, say, FOV, that is field of view, you might have to, say, go on a back foot for your resolution. Or if you need a high resolution camera, um, you might have a limited field of view. So this can be a situation where you can have a car like this, and right in front over here, you can have a very high resolution camera which will collect the information for, say, a limited field of view. But this information is really important for us. And then you can have another camera, say a low grade camera, which has a large field of view but a limited range. Everyone able to understand what kind of thing I'm talking right now? So are you able to differentiate between these two cameras? These are same cameras, but it is giving me different kind of inputs. And then your deep learning algorithm will be designed accordingly later. Yes, no, maybe. Are you able to follow me so far? Let me see how many participants are there. Yeah. All right. Um, good. Okay, finally I figured out how to navigate with WebEx. Good. All right, coming back. So this is a single camera which is doing our job right now. But what if we have two cameras? If you have studied, say, computer vision, you must have seen this kind of example where you have a stereo sensor, which is like multiple cameras attached on a car. So here I have one camera, here I have a second camera, and the images from both these cameras are stitched together. So let us say this is my image one, this is image two, and what I do is, using, say, stitching algorithms that we have in computer vision, I will be capable of, say, stitching these two images and having a larger field of view, and even that is possible. In fact, um, have you seen this kind of example in your day-to-day life uh, using the devices that you have around you? Have you seen this kind of example? Yes. I will actually show you this algorithm tomorrow of stitching images, and how we can do that using, say, computer vision algorithms. And if possible, let us see if deep learning is required over there or not. But it's still an example of, say, computer vision and automation over here. Okay. So have you seen this example in your day-to-day life? Have you taken panorama pictures in your mobile? Anyone? Yes. Great. So that is one of the examples of doing the same, or maybe in order to understand the depth of a particular object. Um, do you see the latest phones that we see around us have multiple cameras on the back? Let me just show my phone immediately over here. So, hmm. I'm turning on my camera. Yeah, over here. So here you can see that there are multiple cameras on the back of my phone. Um, Someone asked me, why do we have this many cameras? What kind of applications are there? So you must have seen that there are some algorithms or applications in your phone which are capable of telling you how much depth a particular object is present right now, and you can actually easily see that uh, the difference between two objects in terms of their distances, how close an object is. Perhaps in our day-to-day life, that might not be a very crucial application. It might be a fun application, but for a car, do you think this is a nice application or a good to have application at the end of the day? In an autonomous vehicle, yes. We need to understand the depth of an object so that we can take actions accordingly. And then there are computer vision algorithms which are capable of doing that. So we generally take that into consideration. If you see a gray box on my screen right now, which is like the chat box, I'm actually monitoring the chat on the left hand side. Okay. Yeah, coming back. So here you can see this is one of the kind of exteroceptive sensor, and we'll see algorithms for this kind of applications eventually. Then you have this lidar sensor, and I will be giving you a small homework today. um, I would rather ask you to read some documentation or watch any fun video on LiDAR, which is available on the open domain like YouTube, any Google any website which tells you about LiDAR. Even Wikipedia page is sufficient for me. I would like you to understand how LiDAR sensor work. Will you do this as a homework for me? Say 10-minute activity for tomorrow's session, because I will actually demonstrate how you can do or design a deep learning algorithm where you will feed LiDAR data and take some action. Um, I also have one more question for all of you. What kind of, say, inputs you have worked with so far when you are designing or designing a deep learning algorithm, whatever deep learning algorithm you have designed? What kind of inputs you have worked with, or say, information you have worked with so far? Is this only images? Text? Okay, text is nice. Apart from text and image, anything else have you worked with? Anyone else in the session? So I would rather show you tomorrow how can we take, say, a numeric data, feed it inside a deep learning algorithm, and still detect what kind of object is present in front of us. Okay, so that is a kind of nice example that I have prepared for you, and I will be demonstrating that tomorrow. Okay, so lidar AI. So I will say collect lidar data, train my neural network, and then feed the real-time lidar data into our neural network and take some action. So I will actually show you what I'm planning to do for you. And for that, there is a homework which I expect all of you will do by tomorrow. We'll see how we can take lidar data, feed it to a neural network, and detect the object which is or obstacle that is standing in front of our car. Okay, so we'll see some fun application like this by tomorrow, and this is how lidar sensors look like. What happens here is this is a motor which is rotating continuously, and the light is being transmitted by the sensor and captured back, and then you try to understand what is the distance at which a particular object is present. So we actually measure the depth of a particular object and create a 3D map around our ego vehicle to look understand the location of this car at a given point of time. And as I mentioned a few moments earlier, see, the technology is limited by this rotating motor and how quickly this data is collected. What if I have a solid state device which does not require rotation of my sensor, and say it will have, say, transmitters and receivers at every point, and this will make your output a little faster. Okay, so this is a work in progress in automotive industry right now, and maybe in future you will see more reliable lidar. In fact, if you saw um, this latest marketing video of Apple phone, that is iPhone, just a few days ago, there is a lidar sensor on the iPhone as well, the latest one. um, the only application that they're using is to improve the quality of an image over there, but whatever, the point here is lidar sensors are getting cheaper and cheaper, and this will ensure that eventually we will have a better autonomous vehicle at the end of the day. So I would like all of you to just read how the sensor work. So tomorrow we will see how we can design an AI algorithm for an input that is generated by lidar. Okay, so that's one action item on your side. And then we have this radars, which is like a robust technology. In fact, radars are almost half century old now. So you can actually see this kind of applications which are really matured, and they were able to successfully get it down in a compact way on an autonomous vehicle, and now you can rely on that as say input coming to our car. So it is used for object detection and relative speed. So you don't know whether you have a car or a pedestrian, but at least you can understand that there is someone um, in front of us, and accordingly we'll take the action. And this is a nice zone where antenna designers are also working today, and you can actually see this kind of applications, how they're designed. In fact, I have taken this as this image from a commercial product which is available on Bosch website. You can take a look at how this radars work, and how the data is produced. I'll see if I can demonstrate a small application on this, but I don't think my computer will be capable of handling that kind of simulation. But I'll try. I'll see if I can demonstrate something like that to you. Of course, we need very powerful systems for designing this kind of applications. So yeah, that is also one technology limitation that we have. And then finally, we have our all weather stable ultrasound sensor where sound is transmitted and it is received back. So it doesn't matter if there is a fog, it doesn't matter if it is night. You can always rely on your ultrasound sensors where uh, at least a small distance is continuously monitored, and this can be used in parking kind of applications. In fact, this is a robust technology which is already popular, already available in your car. In fact, you can see the small dots in your car, in the rear side of your car, and you can see that how these applications are already popular in the market. You can listen that beep sound continuously. So if you're getting closer to an obstacle, continuously the frequency of that beep sound is increased. So this is one of the popular applications. We can actually incorporate this in our AI algorithm eventually, and start using it also. Okay, so all the sensors that we saw so far are what kind of sensor? Exteroceptive, which is monitoring our surroundings. Then there is something called as proprioceptive, or say a sensor which gives us information, internal information of a car. And what kind of sensors do we have? GNSS and IMU. Okay, so it is like Global Navigation Satellite System, which is a product of say US Defense, and then you have IMU sensors, which are also cheaply available in the current scenario, but of course they are not using the low cost ones in the car. But anyways, the kind of information that you get from this is the acceleration of a car, the position of a car using GNSS, or the velocity at which the car is moving from point A to point B, the angular rotation of your car. You can also find out where your car is heading, at what speed, using GNSS and IMU together. So this is a kind of sensor fusion application that you can see using this proprioceptive, and it is giving you information about the car itself internally, and it is not going outside. And then you have your classic odometers, which are like um, second, which is giving you information about the speed and the position drift for a car. Okay, so this is also a proprioceptive sensor which is used in a car for say AI algorithm. So when you say you are doing perception of a car, it's not a single application or say single sensor which is giving you information. It's a collection of all the sensors like video camera, lidars, which are this is the old popular radars, which sorry lidars, which are rotating ones. I will show you a video on how this look like. And then you have radars, you have a central computer. In fact, the modern car is like a set of computers on a car which is taking an action. So this is what you have, and then you have odometer sensor, ultrasonic rear camera, GNSS. You have IMU also, which I think which is not available in this image. So all this together are collecting the data. Let us say you have stream of data which is time stamped, and what you do is you fuse all the inputs together. This is an application called as sensor fusion for your autonomous car, and this data, fused data, is fed into a neural network which will give the control signal, and accordingly your control action will be taken. Everyone following me until this point, any questions, anything you would like to ask me? Oh yeah, I'm continuously talking, so yeah, do let me know. All right, let me show you a video, a really nice video of a lidar sensor. So here you can see the lidar sensor, they're really moving fast. Then you have radars working. So the output of lidar somewhat looks like this. Yeah, this is the exact way in which lidars produce an output. You can see that in say any design or say development tool like MATLAB, or even if you're using say some open source tools are also available. There's Carla, where you can actually simulate this kind of algorithms. So yes, this is how the lidar output look like. Okay. So just a question: are you at least enjoying this session so far? Any questions, or say any random comment that you would like to give us? I mean, I'm just giving you information, as much information as I can. Tomorrow we will see definitely some AI algorithms around this. But before I do a deep dive, I would like to tell you what kind of sensors are present in a car, which lets you do some few things. So this can be a very good input for all of you. All right, nice to see that people are following me. All right, so let's go ahead. Let's change our gear. We have now tried to understand how perception works. We understood what kind of sensors are present, what are the goals of perception algorithm, and what will be the final output, or where the output of your perception will be given. So where part we will see as an AI algorithm eventually, but now you know how perception is done. Then there is something, the part on planning of a car. What all things needs to be planned in a vehicle? Okay, because see, eventually we are saying that we will be designing um, an algorithm that will take some control action. But are we going to take the control action directly? I mean, there needs to be some planning, right? We'll see that planning part over here, how planning can be done for a given situation. So there are three types of planning, like say long term, short term, and immediate. Okay, so long term means, let us say I have to travel from Mumbai to Pune, or Pune to Mumbai. um, I know that, hey, this is the route which is good one. This is the time in the morning, so I should take a particular road. This particular road has enough amount of tolls, so instead of this, I would rather take the other route. This happens a lot in Pune, where I have shifted recently. In Mumbai, we just have this toll near Vashi. That's it. Sorry, I just got lost. But yeah, things like that can be planned when you're having this long-term planning for your autonomous vehicle. When you have short-term planning, whether I should take left turn or I should take a right turn, on the basis of that, whether I should change my lane. If the car in front of me is moving really slow, I would rather change my lane and come back to the original lane. So that comes under short-term decisions. and then immediate decisions that you have to take on a given scenario, like whether I should accelerate or not, whether I should apply a brake. Like say a pedestrian jumps on a road, or say I'm driving at a very high speed and suddenly there is a say animal running on my road. I have to immediately apply my brake, or say there's a dog running behind me. I would rather accelerate and try to run. Sorry. So that is a situation that we have to take immediately. We cannot wait and take that action. So this comes under planning a vehicle. And see, these are the actions that we take as a human. We have to also make sure that even a car is capable of taking all these actions by a systematic planning. And I will actually talk about one nice application in few moments where you will see how much planning is actually required for a simple maneuver a car is supposed to do. Okay, so let's jump into it. Um, so this is a choke, say a simple case study of a road which is just 2 minutes away from my home. It's near Airport Road. So here, this is a place where we have maximum traffic in the morning, and I try to avoid this road as much as I can. But here you have a car which is say coming from this road, and then you have to take this action of entering or taking a left turn. I would say I'll think like a human now. Let us not think in terms of autonomous driving. Okay. Um, Early in the morning when I do travel from Mumbai to Pune, and my home is around over here. My previous office was used to be somewhere here, which is a nearly 10 minute distance for me. But the thing is, early in the morning when I came here, I avoided this road and I had to take the left turn action, and then again I had to take a right turn action to reach my home. This is a place where I had to take a lot of decisions. Okay, and we'll see how we can break down these actions as a human. So when I'm taking a left turn, sorry, I'm changing my lane, which is not allowed. There's always a policeman standing over here. If I take this, I will be fined heavily. So I would rather erase this path. Let me take a proper turn. Yeah. So I am traveling on this road and I have to take a left turn like this. Oh, only for taking this simple action, I have to take so many actions, or say do so much planning. First thing that I will do is check the traffic light over here. Okay. Then there are few people who are not intending to take left turn, but who still make sure that their vehicle is on the leftmost side of my car, sorry, on the road. So I have to actually go on the right and then take a left turn. I mean, there are situations like this happens in Pune a lot. And then let us say there is a car, and I'm not allowed to go on the left turn yet. There is a signal which does not allow me to go over here. And there is a series of car which is standing over here. So I have to slow down my car and come stop at this position. Okay. So this is one of the actions that I might take. Um, well, this is a busy road. There are a lot of people walking around, jaywalking. Is something that happens every day. So I have to stop before some pedestrian comes. Then there is a zebra crossing over here, which is completely faded out right now. But yeah, let's assume that our municipality actually redraws that zebra line properly again. Let us say there is a zebra crossing, and or say pedestrian crossing in simple words. I have to stop my vehicle if there is, say, a red sign over here. So I have to stop before that and not after that. This is one. Let us say there is someone who is not driving properly, so I have to again slow down. So that is one situation. If there is no zebra crossing, I have to assume using my GPS positions whether this car has to stop over here. Okay. So how many actions? A simple left turn. Okay, early in the morning I have to travel from Mumbai. I've traveled all the way from Mumbai to Pune, and I'm almost reaching my home, which is over here. And I have to take a left turn and then a right turn like this. This action require how much of planning? 1, 2, 3, 4, 5, 6. Imagine how or what kind of AI algorithm you have to write to mimic this human action that generally we take. Are you able to relate with this, all of you? So all of us drive our cars, our bikes at a point of time in a day, and these are the actions that we human take. We have to train an algorithm to do this action for us. Imagine how complicated such kind of task can be. Okay. Um, are you able to relate with it, all of us, all of you? You can put it in the chat box. What kind of actions will you take for say just crossing this road? Okay, so I will put my chat box on the right hand side, and let us delete everything from my screen. There's an eraser, too much drawing over here. Yeah. So let us say instead of this road, I can also go my home from like going up to this road and over here. Can you tell me, all of you, in the chat box, can you please tell what kind of actions are you going to take for just crossing this road? You can put that in chat box. Come on, let's make it interactive. A simple action of crossing the road by a car. Anyone? Chat box, please put your strategies or plan for crossing a road using a car as a human. See left and then walk away, then see right. Okay, slow down. Yes. So that's a good step that you will take. Slow down. What are you going to check continuously or monitor something continuously? Okay, check zebra crossing. Check the traffic. Good. There will also be traffic sign, right? A traffic light. We also have to check that. I know in Mumbai it is the pedestrians and the people coming from the opposite lane. They are really careful of all the traffic symbols. But one more challenge that, because we are talking about my current location, there is a situation where although you have a permission to directly go in a straight line over here, and there is a green light over here, there will be still people that will be jumping like this. Okay, or there will be people that will be jumping like this. So we have to also be careful of that. So watching on the left hand side and the right hand side, all these things. Okay, people who are moving on cycles. So not really. uh, uh, so people are now accustomed to understand at what time this traffic police are there, and they have trained their neural networks to say take the decisions accordingly. Yeah. But yeah, so what we have seen just now is even a simple action of just crossing the road is so complicated. Imagine training a computer to do that, a neural network which will take these actions, and what kind of data we have to feed, all these things we have to actually take into consideration from here. Okay, so are you at least able to understand how complex the systems can be? Yes. Hmm. Okay, so thanks. So let us see what other plannings are there. So if there is a pedestrian, you have to stop the car, or which is like a rule-based planning. There are certain set of rules, and you have to follow them, and accordingly, actions have to be taken. So it is this kind of programs you can also put in form of say if-else conditions, and it can be a structured code that will follow a certain rule which is given. Then there is like predictive planning, where say if a pedestrian is jaywalking, you have to carefully stop the car in such a way that if the pedestrian is just say randomly going from left to right direction without any planning. We have to actually slow down the car, see how that person is going around, and then only move ahead of that particular pedestrian. I mean, that kind of situations might arise. And then for that kind of pedestrian, we have to do, say, motion planning algorithms, where you can actually see, or say, sorry, motion tracking algorithms, where you will predict that, okay, with the current trajectory, this person will be this much away in, say, 10 seconds, and I will be. Okay, I will actually draw this. Say this is my car. There's a pedestrian who is just jaywalking on this. And this is my car. I know that in 10 seconds I will be over here. So I will try to do a motion tracking algorithm and predict that in 10 seconds this person will be over here. So I can actually cross the road. But if the person is walking like this, I'd rather change my lane and try to avoid him, or I will just apply a brake over here. Okay, so this is kind of a predictive planning that you can have using your autonomous driving algorithm. Okay, then we have the last step. Localization is something I will talk about tomorrow, if or else we can actually avoid that, because this is a little out of scope of our current discussion. But we can definitely talk about the control algorithm. Okay, and control algorithm, I will actually demonstrate something, a small demo which I'll build right from scratch in front of you. I can show you that. So this control algorithm will be for adaptive cruise control, which we discussed just a few moments ago. And for this, what I'll do here is, I'll design a plant of a basic vehicle using a first order differential equation, and then try to control it using PID algorithm, and then mimic a situation where you have to suddenly apply a brake and see if the car is capable of applying the brake or not, or say come down to stop position or not. Are all of you excited to see this application? I would at least need 10 likes, sorry, 10 yes in the chat box to start with that application. So 1, 2, 3, 4, okay, 5, 6. This will ensure that people who are not interacting will interact. So I only have 6 people saying yes. Others, all right. This is a good threshold for me. I can go ahead. Let's not stall everywhere. Okay, good. So just give me a second. I will connect a second monitor. Just give me a second. I am realigning my hardware a little bit so that I can parallelly. All right. Good. Thanks for your patience. Let us get started. So I will end the presentation over here. There is an exception. So for this application, we have a simple physics model. Okay, so this is a longitudinal control example that you are about to see. We will create a very simple model of a car, which is like mv dot plus bv equal to u. So mv is the mass of my car, and v dot is the acceleration that we are applying to this mass. And then there is an opposing, say, force on my car because of the damping coefficient, and this can be, say, coming from air resistance, gravels on my road, things that are slowing down my car a little bit. And what I'm supposed to do is maintain the speed of the car, which has been given to me as an input. So the input to my system is this u, that you can see over here, and this u is supposed to be given as a reference to my system. Okay, so just give me a second. I would rather draw this for you so that you can see this in action. So I can use this empty sheet as a canvas over here. Okay. So we will now relate this entire algorithm in terms of a control system design. So you can relate this with something that you see in your day-to-day life. Like someone said that they saw this application in a Creta car. So here you have adaptive cruise control or automatic cruise control system. And what you're supposed to do is maintain the speed of car at a speed that is provided. So let us say I have programmed my car to come at a speed of 80 kilometers per hour. Okay, or I can say 40 kilometers per hour because this is the maximum speed limit on a urban environment. And what am I supposed to do is I will first design the dynamics of my car, which is going to be the plant that I will be controlling eventually. Okay, and then you have a reference. So this reference is like 80 or 40, which we are giving. So this reference is changing as per the driver's requirement. Okay, and if you put it in the say adaptive cruise control or say autonomous driving environment, this is a reference that is generated by our AI algorithm, and I'm actually showing you the output, how the control action will be taken. So this is a changing reference. Let us assume that this is ref written because I'm drawing using mouse. Okay, and this reference is a tunable parameter. Let us assume this is my tuner. Okay, we have a speed of 0 up to the speed of 100, and I'm changing the speed, regulating, and this output comes from an AI algorithm, and I am giving this reference to my plant, and I'm expecting, plant means my car, and I'm expecting that the speed of this car is supposed to be maintained. Now, if I have this as an open loop control system, I'm pretty much sure that this system is not going to work properly. So if you go back to your classical control system algorithms, this will look like a block diagram of your system where you have a feedback which is coming from my odometer, and this feedback, can anyone help me? What kind of feedback am I going to give? Is it going to be positive or negative feedback? Any random guesses? What will happen if I give a positive one, Indrajit or Indrajit sir? The system might go unstable, right? So we'll have a negative feedback. So I'm giving this as a plus input and minus input. And over here, I will put my controller. Okay. So this controller is nothing but a microcontroller or say ECU in a car, which will take the action for you. Okay, and that's how we will be designing our system. So first what I'll do is I'll design the plant, give a reference input, show you how it is failing and why do we need this PID controller which will take the action for us. Okay, so today we'll see how output of a system like this look like, and then tomorrow I will teach you how this references are generated for us. Okay, but for now let us see how control algorithms work over here. So it's a mix of say your um, computer vision, AI, deep learning, control system, embedded systems, all of them are working together. In fact, for radars and lidars, or at least for radars, you require antenna design and say signal processing, FPGA program. All of these things come together. In fact, you also require MEMS for your say your airbags and so on. Someone is trying to ask a question. Who is this? I think it was accidental. Or was there a question? I guess it was accidental. Okay, let's come back. So here you can see that how this kind of application can be designed. So let's go into MATLAB now. In MATLAB, I will start with Simulink. So if this environment is new to you, this you can my current all the here. And today single project which is being designed in the current location. As I'm an alumni of Lateral Institute of Technology, a lot of professors and my colleagues have seen me working in MATLAB a lot. Eventually, uh, uh, this has been the part of my career day in, day out. So, yeah, just a tribute. Yes, here I will start with a simple project. So, a new can directly jump into things, but I generally prefer the method of working with a project, which ensures that certain things are well aligned right from the beginning. So I would say adaptive cruise, FDP. Okay, simple that you voice actor, which a few moments ago because yeah, it was not audio issue. I hope so. I hope it is better now, Chidna ma'am. Yeah, I will also open Simulink in the background. Simulink takes some time to load. So let us load it quickly. Great. It's not breaking. Actually, I am slowed down a little being loaded in the background. So that is the reason there is a break. Sorry for that. As we know, MATLAB is a heavy software, so it takes a little time to load. Or the voice is breaking when I'm talking. How is it going? So I will now onward say that I will go on mute for a few seconds. I won't speak, so it will be easier for you. All right, let's save this file in the same location. So MATLAB over here, we can name this as ACC underscore MODL model. Okay, and here we will start with the physics of our model. So here I will put an annotation. So let's just paste it and simple annotation. So for this system, I have certain requirements. So my time should be less than 5 seconds, which means that my system, if I'm giving an input of say 10 meters per second, the car should reach the speed of 10 meters per second in 5 seconds. And then this is the formula which represents my system: mv dot plus bv equal to u. Just a second. And this is the variable that or the values that we have. Let me just increase the font size so you will be able to see this properly. And yeah, I hope the formula and all the parameters that are with everyone. Yes, start designing this. So if you're new to Simulink, programming language that contain a lot of libraries, and this library contains that can be used to model and simulate a dynamic system. Also, eventually I will show you how we can generate a code out of that, which can be deployed on an actual car and you can run it over there. Okay, so let's get started. So here I have this particular signal, mv dot plus bv equal to u. Let's rearrange this. I will do it verbally over here. So I will take this on the left hand side and send bv to the right hand side. So it will be mv dot equal to u minus bv. Okay, so if I have a signal, say MV dot, it has two inputs that are being added, which is first I have U, which is my say step input. I can generate a scenario, say fake scenario, emergency brake kind of situation. We have this BV coefficient, which is coming from our equation. We have MV, which is an output. How am I going to get V dot of MV dot? Any guesses? By multiplying it by 1 by M, right? So M is 1000 kg and B is 50 Newton seconds per meter. Let us initialize those values. 1000 and B equal to 50. So this is the values for my car. Applying Newton's second law, I was able to get this equation. And now what I'm going to do is I will use this variables which are created in workspace in my model. So I'll just call them. So here I have an gain, and the gain value is around say 1 divided by M. Okay. So the output here is V dot. Okay. How would I get a V out of V dot? Or how would I get, say, convert V dot into V? By which, say, mathematical operation can I do that? Anyone? Any guesses? I will integrate it, right? Okay. So, add an integrator. Okay, just a second. Yeah. All right. Here we have our integrator. Okay, and this output is my V, the velocity that I want to control. Okay, so I would visualize this output on a scope. So scope is like our oscilloscope where we check our signals. This is like a virtual scope that I have. So I would call it a scope. It's called scope. My system is this way. Okay, good. So now we have a scope and I have a V signal over here. So if I name the signal V dot, or I would write okay. So this is this, and this is the acceleration. I have to multiply this V by B, or say minus B before I feed it over there. So I have a gain, and the gain will be value minus, and let's rotate it twice. Okay, and then I have my reference input. So I will take a step input. So the step input is the speed that we want at say 3 seconds is going to be say 30, something like that. So let us say step time is going to be 3. Initial value, let us start from 0. Let us see how the car is working in initial condition. 0, and final value will be say 100. 100 meters per second. Let's see how the system will work in this situation. And so this is just plant with this the control system classical diagram. This is just my plant which is designed, and we are seeing how the system is working under a given situation. So because of loading, we'll also feed another input to see look like in a here we have scopes where we are looking at. I assume that the scope is visible to everyone. The step given that the vehicle should reach the speed of 100. Let us see if we are able to do that. The kind simple step to do. Is the velocity not really, right? Hey, are you guys following me on this one? So I have a simple dynamic model of a car which will be controlled by our control algorithm. Okay, it is like my plant which I will control. I'm not going to get into the longitudinal control, lateral control, or say a complex yaw pitch roll control model of a car. I'm just having a simple one-dimensional mod equivalent, mathematical equivalent of a car, which I'm being trying to control over here. Seeing the complexity of this say limited time that we have over here. Okay, everyone able to follow the equation? So let's assume everyone is following. Let's go. Seeing the paucity of time that we have. So what I will this this and this is my plant model. Okay, so this is my system. This is my plant control, and over here for this plant feedback. Okay, and for this the symbol is going to be plus minus because we don't need negative feedback. Or sorry, we don't want feedback. And let us just keep like this. Step input which is given away. The feedback comes from the output of my plant. Created a simple feedback loop for my system. Okay, don't improve the output, but please the output is still same because there is no control. So I'll use or I will get started with simple P controller for the system. So a P controller is nothing but a simple gain that we can add in our system. And if I say give a gain over here, and now you can see that we're at least reaching 50, which is good enough, but not sufficient. I mean, actually not really good enough. It is improving, is what. Anyone? Any guesses? Random guesses. I would rather have gain, right? So instead of 100, let's make it 2000. I is giving a randomly large. I'm just trying to demonstrate something to you how P control. So what's happening? Proportional trying to steady value by increasing the over here using this really high gain. Only P gain. What is this disadvantage by comparing answers? Steady state error, which will always okay. This is a disadvantage. P control. Because of paucity of time, I won't design a integral and derivative controller from, but I would use a ready for that. Okay, so let us say there is a PID block that we have over here, a PID controller. And in this case, I would use this rate as it is for my system. Yeah, and in this add change the gain. PID is represented using this equation. I can have say ideal form or the parallel form for this PID controller. When I say ideal, your P is followed by I is followed by D, like I and D over here, but instead of this, I'm using parallel. So P is added to I is added to D, and D also have this because of this equation which comes like 1 upon n upon n plus s is actually a small filter that you have, and if you say simplify this equation, this s will come on the top, and this s into d is like the derivative controller that we are adding. It's like a derivative block. So that's how we are thinking about this derivative over here. And what I'll do is I'll just change the values of PID. So my P is 100 and I will be significantly good value. D, I won't get started with it immediately, but change the values and show you how this is like. Okay. So over here, it's the response that I wanted. Okay. Range that I want, which is not ideal, definitely. So there are, I can also say my proportional gain can be instead of 100, I can make it 600. And integral gain, let us make it say 50 is a large 200. Let us get started with a simple value like this. And so over here, that then the system is stable. With this PID values, I mean, there are there are say conventional ways to do it, but then there is one more way which is getting popular in the industry, which is automation in tuning your PID values as well. Okay, so this filtration, sorry, I forgot to tell you, this is for this low pass filter we add at the output along with the deep derivative frequency noise from our derivative. Else, the derivative will not work the way we are expecting it to be. Okay. Yeah. By the time this app is opening up, I will show you this. I think if you're any previous session or any MathWorks event before, you must have seen this PID tuner app before. So this what this app will do is it will automatically ensure that you think like a control system engineer. You think in terms of the input and output responses. The P, I, and D gains are automatically tuned for you by the app in the background. Okay. Hopefully the app should have opened by now. I know I'm putting a lot of at this time. So yeah, it's opening up. So there will be a small pause in between my audio until the things load. All right, this is a too much of a pause. So um, okay, finally this opened up. So what you can see here is the response that I have right now, and if I PID gains, this will be the response that I will get. So I will open this button called show parameters, and over here I will compare this with the requirement that have been provided to us. So I have rise time, overshoot, and steady state error, 5, 10%, and 2%. So let me see. In the current situation, I have overshoot as a tune block. The overshoot is around 7.86. Is it below the level that I want? Yes, it is. And the rise time is 17.3 seconds. How much do I want? In tuned, okay, it is actually larger, which is not expected. I want it to be less than 5 seconds. So I will make it faster. So now it is 1.7 seconds, as you can see over here. And the overshoot is 10.9. Okay, I can make the system a little more robust. So overshoot is 9.7 seconds and rise time is around 1.97. I'm actually playing between this trade-off. So now my rise time is supposed to be 5 seconds. I am almost over there, as you can see over here. 5.25. I can make it a little faster yet. Okay, 4.81, decent. Overshoot is 8.2. And because of my eye controller, the steady state output will be 0 eventually, is what I'm expecting. And the tuned response, these are the values, ideal values that I have obtained. Okay, earlier it was something I'm trying to tune manually, but over here the app is helping me out. Now I will update these values, and you can see that these values are going to get updated over here. Okay, good. And then I will click on OK, which means that these values are now updated in my PID controller. And if I run this system, eventually see this is actually in 10 seconds we are able to reach a point where the car is reaching up to the speed of 100. Okay. Let us run the simulation for instead of 10 20 seconds, and settling down. What if we try to mimic a situation where you have or applying a brake immediately? Okay, so initial value I will say of my car was 60 meters per second, and I want the final value to be 0. It is like a step down. So suddenly at say 5 seconds, I'm applying a brake on for my car, and if I click on apply and OK, set on signal. So we are mimicking a situation of applying a brake, and we'll see how my system. Okay. So earlier and initial condition was around 0 for my car. Okay, so I would rather give the initial condition of say 60. No, it was 0. I can make it 60. So we can say that the car was at a steady state. And we say that the car is already at running at a particular speed, and the brake is applied, and in say seconds, you will be reaching to a point applied. In 10 seconds or at least 5-6 seconds, you are to a point where your car is coming at a halt. Again, if we tune our PIDs properly, your car's output, and you will be able to see how control action is taking place. So again, your autonomous vehicle is not just a AI algorithm which is working. AI algorithm working along with some physical plant with a controller hardware, and all of them as a mix of together is going to do some action, and that's how things work in an autonomous vehicle environment. I think we are sharp at almost 7 o'clock. It's like 6:58. So good question, Indrajit sir. It is not going to be say OPAM based. In car, there is something like an ECU, electric control unit, which is at the end of the day a microcontroller. Most popularly, Renesas, NXP, Texas Instrument controllers, which are popular in automotive industry right now. And these PID algorithms will sit in that ECU, where it will monitor various feedbacks which is coming from our sensors, and accordingly the action of controlling your car will be taken place. Okay, so any questions that you have? Did you enjoy this part, the theory of autonomous driving and some practical applications, and how tomorrow we will see how we can merge them together. Okay, I will actually show you some fancy application like detecting an object, and I would this in if my computer allows me. Um, how you can actually do say control using your 3D simulation. So this is your ego vehicle, and what happens here is it is checking all the possible paths. Accordingly, the actions will be taken. So it is also predicting what will be the position of a car after a few seconds when we are overtaking them, and so on. Okay. So I would rather show you this kind of actions when you have to apply a brake, when you have to do steering. So we'll see applications like this. All right, so it's 7 o'clock. End of our part one of the AI case studies. I have created enough background for you guys to understand the complete environment in which AI algorithms will work in a car. And tomorrow we'll go ahead with some advanced applications where we'll visualize this in action. Okay. Any questions before we end this session? Anything you would like to ask me? Ranut sir, over to you.
हाँ पवन सर बोला.
So any ending note for day one part one of our session?
Yeah, I'm waiting for if there are any questions from participants if they want to ask. So no questions.
So I guess then we can conclude the session, sir, as we are having Pawan Kumar sir tomorrow as well.
Yes.
So thank you, sir, for making us aware about autonomous driving, which is one of the key application areas of artificial intelligence. So we are hoping for some more nice things at the sensors and everything. So hoping to see you tomorrow with some additional things that we you have taught us today, some additional uses of how the things work and all.
Right, thank you, ma'am, and see you tomorrow.
See you tomorrow, sir.
And
Thank you
there's
very
a
much.
small homework again. Please read about LIDAR. I would like to show you how it does work with AI algorithms. So there's a 5-minute task for everyone. All right,
Yeah.
thanks, and see you
Okay,
tomorrow.
sure, sir.
Bye.
Yeah, participants, now tomorrow, day after tomorrow, in fact 2-3 days, you will have similar kind of sessions, remember. So it's a multidisciplinary approach. So if you are thinking that only collab notebooks will be there, so that are not going to be there. Over. Jitna collab ka karna tha khatam ho gaya. So now you will have a real life application. Pawan is day in and day out working on autonomous driving cars at his industry, KPIT. So it's a good resource person for us. Similarly, we will have Govind sir tomorrow. Day after tomorrow, entire session is by him. So you will find now a lot of mix from other branches like electronics. So you will see a lot of embedded electronics, machine learning, AI. So exciting journey. Actually, this is why we have proposed this entire course. So we are nearing the end, but will be an exciting applications for all of us to study. So please participate and join on time. Okay. So thank you very much. Thank you, Pawan. Thanks a lot. Very nice, interesting discussion you have done. Looking forward for tomorrow's session as well.
Thanks, sir. Have a good rest of the
Yes.
day. Bye.
अच्छा पवन जस्ट अ मिनट बाकी लोगों को जाना है जा सकते हैं बट आई कैन डिस्कस एटलीस्ट दिस मैटलैब आर यू यूजिंग मैटलैब एट केपीआईटी एज वेल
Yes, sir.
फॉर दिस वर्क यू यूज मैटलैब.
Yes, sir, we use MATLAB, and there is another alternative for MATLAB called Carla along with Python. So instead of model-based design, you can also use Python coding for that. The only advantage that you get MATLAB is there's a block diagram-based language and automatic code
अच्छा
generation.
अच्छा
So we use either of them.
अच्छा ठीक है. So we will, since participants have left half of them, so we'll have tomorrow more discussion on this now. Okay. Yeah. So
MATLAB is
now,
like my entire career is dependent on that.
chalo. Okay. You have a nice time.
Okay. Bye.
Okay. Chalo. Bye. 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 So participants, I'm closing the session now.
Sir, it is again it's showing live.